Hello students, welcome to this final lecture of Unit 1 Solutions. In today's lecture, we will discuss about abnormal molar masses. Since this is a final lecture, we will summarize all the previous lectures and work out examples, previous year questions, multiple choice questions and exemplar problem. So this is very important and you please listen to it very carefully and note down all the important points. I welcome you once again. Abnormal molar mass. For substances undergoing association or dissociation in solution, the molecular mass determined by studying any of the colligative property is different than the theoretical expected value, and the substance is said to show abnormal molar mass. That means when the substance undergoes dissociation or association, then the molar mass is different than the theoretically expected value. Such substances are called abnormal molar mass. Abnormal molar masses depend upon the total number of moles particles after dissociation or association of solute molecules in solvent or solution. Before we discuss about association or dissociation in detail, let us quickly recap what do we mean by cations and anions. When ionic compounds are dissolved in water, they dissociate into cations and anions. Cations are ions that are positively charged. Anions are ions that are negatively charged. Ions are charged atoms or molecules. If a balanced atom loses one or more electron, it will become a positively charged cation. If a balanced atom gains one or more electrons, it will become a negatively charged cation. Dissociation and association of solutes. First, we will discuss about dissociation of solutes. There are many solutes such as organic acids, salts and bases when dissolved in water dissociate into ions. For example, when 1 mole of NaCl is dissolved into water, it dissociates into Na plus and Cl minus. After dissociation, there would be 1 mole of sodium and 1 mole of chloride ions, which are released in the solution. Thus, we get 2 moles of particles. Before dissociation, there was 1 mole, and after dissociation, there are 2. Thus, after dissociation of NaCl, or that is true for other solutes such as KCl or any other solute which breaks into ions into water, and the boiling point of water increases. So in the case of dissociation, boiling point of water increases. Please note down. And when molar mass is determined experimentally, it always comes that the molar mass is lower than the expected value. Further, we'll discuss about association of solutes. There are many solutes when dissolved get associated into the solution, and this decreases the number of moles. So when they come together, 2 moles will become 1 mole. So which increases the molar mass of the solution than the expected value when determined experimentally using the colligative properties methods. For an example, acetic acid, that is ethanoic acid, is dissolved into benzene. Molecules of acetic acid gets associated or dimerized due to hydrogen bondings. These are hydrogen bondings and number of particles reduced. The chemical reaction is shown on the screen above. This happens generally in the solvents having low dielectric constant. This process increases the molar mass than expected value when determined experimentally. Van 't Hoff factor. In the year 1880, Van 't Hoff introduced a factor I known as the Van 't Hoff factor to account for the extent of dissociation or association. This factor I is defined as I is equal to normal molar mass divided by abnormal molar mass. That is equal to observed colligative property divided by calculated colligative property. And numerically it can also be written as total number of moles of particles after dissociation or association divided by number of moles of particles before dissociation or association respectively. Here abnormal molar mass is experimentally determined. Molar mass and calculated colligative properties are obtained by assuming that the non-volatile solute is neither associated nor dissociated. In case of association, value of I is less than unity, while for dissociation it is greater than unity. For example, I for aqueous KCl is solution is nearly equal to 2, while value for ethanoic acid is in benzene is nearly 0.5. Van 't Hoff modified the equations for colligative properties as given below. So modified equation for Van 't Hoff factor for colligative properties are relative lowering of vapor pressure of solvent is P1 naught minus P1 divided by P1 naught equals I into N2 by N1. Here P1 naught, P1 and I N2 are all defined as earlier. I is the Van 't Hoff factor, N2 is the number of moles, N2 and N1 are number of moles. Similarly, the elevation of boiling point becomes delta TB. That is, elevation boiling point is delta TB equals IB into KB into M. Here M is the molality, small m is the molality. Depression of freezing point delta TF is modified as delta TF is equal to I into KF into M. Simply in all these cases, the right hand is multiplied by factor I. And finally, the osmotic pressure of solution is pi equals I into N2 RT divided by V. Now we will derive expressions for dissociation and association of solutes. Dissociation of solutes. Consider an electrolyte A subscript S, X and B subscript Y undergoing dissociation with degree of dissociation alpha. So the equation can be written as AXBY dissociates into X into AY plus Y into BX minus as shown on the screen. Therefore, before dissociation, there will be 1 mole of AXBY, and since there is no dissociation, the number of moles on the right hand side are 0. Then after dissociation, it loses alpha molecules and it becomes 1 minus alpha, and the right hand side we get X alpha and Y alpha. So total molecules will be 1 minus alpha plus X into alpha plus Y into alpha. That is this line completely total. That is equal to simplifying alpha into X plus Y minus 1 plus 1 is the original mole. So by definition, I is equal to total number of moles of particles after association divided by number of moles of particles before association. That becomes I is equal to alpha into X plus Y minus 1, this equation, divided by 1. 1 was the before association, number of moles before association. So that formula for dissociation of solutes is I is equal to alpha into X plus Y minus 1 plus 1. Or we can also write a term for alpha. Alpha, the dissociation factor, alpha is equal to I minus 1 divided by X plus Y minus 1. Similarly, we will do the calculation for association. Please note here that in case of dissociation, value of I is always greater than unity. The value of I for aqueous solution KCl is close to 2. Please note for in the questions usually dissociation is not mentioned, that dissociation. We have to presume that when it is not mentioned, it is dissociation only. Association of solutes. For a solute undergoing association, let alpha be the degree of association. So Na will associate to form An. So initially at t equal to 0, there is 1 mole before dissociation and 0 moles after association. That is because there is no association at all. And after association, it loses alpha molecules and hence it becomes 1 minus alpha, and the right hand side becomes alpha by N. Therefore, total will be 1 minus alpha plus alpha by N. So, again by definition, I is equal to total number of moles of particles after association divided by number of moles of particles before association. So, that is equal to 1 minus alpha plus alpha by N divided by 1. So that becomes I is equal to 1 minus alpha plus alpha by N. Or rearranging, alpha is equal to I minus 1 into n divided by 1 minus n. You work out in your notebook these simple calculations and rearrangement. In case of association, value of I is less than unity. The value for ethanoic acid in benzene is nearly 0.5. Please note that in case of association, it will always be mentioned in question that it is association. Otherwise, if it is not mentioned, you can take it as dissociation. The table shows the values of Van factor I. So the salts are shown on the left hand side, the first column. So NaCl, KCl, MgSO4 and K2SO4. For different uh, uh, association factors, alpha values or different values of all value of I is shown on the screen. So 0.1 m, 0.01 m and 0.001 m. The values for NaCl corresponding are 1.87 for 0.1 m and for NaCl for if value of I is 1.94. Similarly for 0.001 it is 1.97. Van factor I for complete dissociation of solute is 2. For complete it is 2. For partial dissociation it is different values are given on the screen. Example: 2 grams of benzoic acid, that is C6H5COOH, dissolved in 25 grams of benzene shows a depression in freezing point equal to 1.62 Kelvin. Molar depression constant for benzene is 4.9 Kelvin kg per mole. What is the percentage of association of acid if it forms a dimer in solution? Please note it is a association. We have to find out the percentage association. Answer: as a first step, note down the given quantities. That is, W2 is equal to 2 grams, Kf is equal to 4.9 kelvins kg per mole, W1 is equal to 25 grams and delta Tf is equal to 1.62 Kelvin. These are all given and you substitute these values in the formula. M2 is equal to Kf W2 into 1000 divided by W1 into delta Tf. This is the formula for molar mass of benzoic acid. So we substituting we get the value as M2 is equal to 241.98 grams per mole. Please note down all the values, substitute in the equation and simplify it as 249.98 grams per mole. Now consider the following equilibrium for the acid, that is 2 into C6H5COOH associates to form C6H5COOH2 as written and shown on the screen in blue color. Let X represent the degree of association of the solute when we would have 1 minus X mole of benzoic acid left in unassociated form and correspondingly X by 2 associated moles of benzoic acid at equilibrium. Therefore, we can write the total number of moles of particles at equilibrium is 1 minus X plus X by 2 gives simplifies to 1 minus x2. This is the total number of particles at equilibrium is 1 minus x by 2. Thus, the total number of moles of particles at equilibrium equals Van 't Hoff factor I. That is, I is equal to normal molar mass divided by abnormal molar mass. That becomes, substituting the values, we get 1.22 grams per mole divided by 241.98 grams of mole. This 1.22 grams of mole per mole is the normal molar mass. This is abnormal molar mass we have calculated in the previous step. Therefore, the degree of association of benzoic acid in benzene is given by the relation x by 2 is equal to 1 minus 1.22 divided by 241.98. That is equal to 1 minus, this value is 0.504. That is equal to 0.496. Therefore, x by 2 is equal to 0.496. So, therefore, x will be equal to 2 into 0.496, that is equal to 0.992. Therefore, percentage of association is into 100. That is, x is equal to the degree of association of benzoic acid in benzene is 99.2%. Next question. 0.6 ml of acetic acid, that is CH3COOH, having density of 1.06 grams per milliliter is dissolved in 1 liter of water. The depression in freezing point observed for this strength of acid was 0.0205 degrees centigrade. Calculate the Van 't Hoff factor and the dissociation constant of acid. Please read the question once again and note down the given values. Let us proceed with the answer. Number of moles of acetic acid is equal to 0.6 ml into 1.06 grams per milliliter divided by 60 grams per mole. That is equal to 0.0106 mole. Let it be N. That is, the number of moles of acetic acid be N. Therefore, molality equals 0. Number of moles divided by 1 kg, that is equal to 0.0106 mole divided by 1000 ml into 1 gram per milliliter. That is equal to 0.0106 mole per kg. Now we will apply the formula. Delta TF is equal to KF into W2 into 1000 divided by W1 into M2. This we have studied in section 1.35, that is equation number 35. Therefore, delta TF will be equal to 1.86 kg per mole into 0.0106 moles per kg. That is equal to 0.0197 Kelvin. So, Van 't Hoff factor I is given by observed freezing point divided by calculated freezing point, that is equal to 0.0205 Kelvin divided by 0.0197 Kelvin. That value is 1.041. That is, I will read again. Vanta factor I will be equal to 0.0205 Kelvin divided by 0.0197 Kelvin divided by 1.041. Acetic acid is a weak electrolyte and will dissociate into two ions, acetate and hydrogen ions per molecule of acetic acid. If X is the degree of dissociation of acetic acid, then we would have N into 1 minus X moles of dissociated acetic acid. NX moles of CH3COO minus and NX moles of H plus ions. Therefore, we can write it as CH3COOH dissociates into hydrogen H plus and CH3COO minus negative. Therefore, N moles of CH3COOH before dissociation are N moles, and after dissociation it will become N into 1 minus X, that into hydrogen plus H plus is NX mole and CH3COO minus is NX mole after dissociation. So thus the total number of moles are, you are adding all this, N into 1 minus X plus X, N taken common, plus X plus X. So this 1 minus X, X plus X equals, simplifying, we get N into 1 plus X. Therefore, total moles of particles are N into 1 plus X. Now, writing the formula of I factor, we can write it as I is equal to N into 1 plus X divided by N. So numerator is number of moles after dissociation and denominator is before dissociation. Therefore, I is equal to N and N get cancelled. I is equal to 1 plus X, that is equal to 1.041. Thus, the degree of dissociation of acetic acid equals X is equal to 1.041 minus 1. That is equal to 0.041. Now, we will write equation for CH3, number of moles for CH3COOH. So number of moles from this line, it is N into 1 minus X. CH3COOH is equal to N into 1 minus X. Here in this step we have written CH3COOH is equal to N into 1 minus X. That is equal to a value of N is 0.0106 into 1 minus 0.41. So this 0.0106 is the N value of N we have found in the first step. 1 minus N, that is equal to CH3COO minus, that is equal to NX. So there again we will write here CH3COO minus NX. N is 0, again value 0.0106 into X is 0.041. Then H plus. H plus is also equal to Nx. So that is 0.0, N is 0.0106 into 0.041. Now to find the value of Ka, we have to use the relationship Ka is equal to CH3COO minus into H plus divided by CH3COOH, that is equal to 0.0106 into 0.041 into 0.0106 into 0.041 divided by 0.0106 in this step into 1 minus 0.041. That is, we have substituted this value 1, 2, 3 here. Therefore, multiplying and simplifying, we get the value as 1.86 into 10 to the power of minus 5. That is the answer. Now let us quickly summarize the contents of Unit 1, that is solutions. A solution is a homogeneous mixture of two or more substances. Solutions are classified as solid, liquid, and gaseous. The concentration of a solution is expressed in terms of mole fraction, molality, and in percentage. So in percentages, there is a mass percentage, volume percentage, and another one which is not percentage is parts per million. Mass percentage is mass of the component in the solution divided by total mass of the solution into 100. Volume percentage is volume of the component divided by total volume of the solution into 100. Parts per million is number of parts of the component divided by total number of parts of all components of the solution into 10 to the power of 6. Please note it is 10 to the power of 6. And by definition, mole fraction represented by letter X is equal to Na divided by Na plus Nb. That is also written as Ni divided by summation Ni. And molarity represented by letter capital M is number of moles of solute divided by volume of the solution in liters per decimeter cube. And molality, small m, represented by the symbol small m, is moles of solute divided by mass of solvent in kg. The dissolution of a gas in liquid is governed by Henry's law, according to which a given temperature, the solubility of gas in a liquid is directly proportional to the partial pressure of the gas. So, mathematically, Henry's law can be written as P is equal to Kh into X, where P is the pressure, partial pressure, Kh is the Henry's constant, and X is the mole fraction. The vapor pressure of a solvent is lowered by the presence of a non-volatile solute in the solution. So, in presence of non-volatile solute, the pressure decreases. The vapor pressure decreases. The lowering of vapor pressure of the solvent is governed by Raoult's law, which states Raoult's law says P1 of solution 1 is directly proportional to the mole fraction of solution 1, and that is also can be written as P1 is equal to, removing the proportionality and substituting proportionality constant, P1 is equal to P1 naught, where P1 naught is the vapor pressure of the pure component, one at the same temperature. In a binary solution, if both the components of solution are volatile, then another form of Raoult's law is used. Solutions which obey Raoult's law over the entire range of concentration are called ideal solutions. For ideal solutions, different formulae are given. That is, P total is equal to P1 plus P2, or it is also written as P total is equal to P1 naught x1 plus x2 into P2 naught. Simplifying all those in different forms, P total is equal to P1 naught plus P2 naught minus P1 naught into x2. For ideal solutions, delta H is equal to 0. That is, the total change in heat is 0. Similarly, change in volume is also 0. The vapor pressure of a non-ideal solution is P1 is not equal to, for non-ideal solution, P1 is not equal to P1 naught x1, and P2 is not equal to P2 x2 naught, because they don't obey Raoult's law. Two types of deviations from Raoult's law are possible. They are called positive and negative deviations. As azeotropes arise due to very large deviation from Raoult's law. The properties of solutions which depend on number of solute particles and are independent of their chemical identity are called colligative properties. Please repeat. The properties of solutions which depend on the number of solute particles and are independent of their chemical identity are called colligative properties. Here, the properties depend on the amount of solute. These are the properties. The colligative properties are vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. So there are four properties of lowering of pressure. Colligative property. There are four. So I repeat, there are four colligative properties. One is lowering of vapor pressure. Second is elevation of boiling point. Third one is depression of freezing point. And fourth one is osmotic pressure. The process of osmotic pressure can be reversed if pressure higher than the osmotic pressure is applied to the solution. Colligative properties have been used to determine the molar mass of solute. Solutes which dissociate in solution exhibit molar mass lower than the actual molar mass, and those which associate show higher molar mass than the actual mass. Quantitatively, the extent to which solute is dissociated or associated can be expressed by Van 't Hoff factor I. This factor has been defined as the ratio of normal molar mass to experimentally determined molar mass, or as the ratio of observed colligative property to the calculated colligative property. Various formulas and relationships are shown on the screen on the right hand side inside box. Please note down all of them and try to understand. Now we will move to the most important part of multiple choice questions. Question number 1. Why is the molecular mass determined by measuring colligative property in case of some solutes is abnormal? Please read the question once again. Why is the molecular mass determined by measuring colligative property in case of some solutes is abnormal? So four options are given. Please read all the four options and choose the correct one. Read it yourself. I will pause for some time. The answer is it is due to association or dissociation of solute molecules. Next question. Which of the following will have the same value of Van 't Hoff factor as that of K4FeCN6? So four options are given. You read it, all the four options. Al2SO4, AlCl3, AlNO3 of 3, AlOH3. So the explanation is shown on the screen. K4FeCN6 gives 4K plus FeCN6 4 minus. Al2SO43 gives 2 Al3 plus 3SO2 4. Hence, option A is correct. Please mark A as the answer. Next question. If alpha is the degree of dissociation of Na2SO4, the Van 't Hoff factor I used for calculating the molecular mass is, four options are given. 1 plus alpha, 1 minus alpha, 1 plus 2 alpha, and option D is 1 minus alpha. So please analyze it. Na2SO4, the chemical reaction is 2 splits into Na plus and SO4 2 minus. So before dissociation, the number of moles is 1, and after dissociation of alpha particles it is 1 minus alpha, and this will be 2 alpha, and this is single alpha. So Van 't Hoff factor will be equal to 1 minus alpha plus 2 alpha plus alpha divided by originally 1 alpha. That is equal to, this is simplifying the numerator, it becomes 1 plus 2 alpha. The correct answer is C. Next question. What will be the degree of dissociation of 0.1 m MgNO32 solution if Van 't Hoff factor is 2.74? Four options are given. Option A 75%, option B 87%, option C 100%, and option D 92%. We have to analyze this question and to find the correct answer. MgNO32 dissociates into Mg2 plus and 2 of NO3 minus. So alpha is given by alpha formula, you have to remember. Alpha is equal to I minus 1 over N minus 1. So I is given as 2.74 minus 1 and there are 3 moles. 3 minus 1 that is equal to 0.87. Therefore, degree of dissociation will be 0.87 into 100 that is 87%. Option B is the correct answer. Please mark it. Next question. Which of the following units is useful in relating concentration of solutions with its vapor pressure? Option A, mole fraction. Option B, parts per million. Option C, mass percentage. And option D, molality. You have to remember and mark option A as the correct answer. So mole fraction is, of all the given option, mole fraction is useful in relating concentration of the solution. Next question. On dissolving sugar in water at room temperature, the solutions feels cool to touch. Under which of the following cases dissolution of sugar will be the most rapid? Four options are given. Sugar crystals in cold water, sugar crystals in hot water, powdered sugar in cold water, powdered sugar in hot water. Please pause the video and give your answer and I will give the explanation. Powdered sugar has large surface area. It dissolves faster in hot water. As solution feels cool to touch, dissolution is endothermic. So dissolution will be favored at high temperature. So option D is the correct answer. Next question. At equilibrium, the rate of dissolution of solute in a volatile liquid solvent is, four options is given. Option A, less than rate of crystallization, greater than rate of crystallization, equal to rate of crystallization, and it is 0. Option D is 0. You have to analyze and mark the correct answer. Please pause the video and give the correct answer. I will give the explanation. At equilibrium, rate of dissolution equals rate of crystallization. So option C is the correct answer. Please mark it. Next question. A beaker contains a solution of substance A. Precipitation of substance A takes place when small amount of A is added to the solution. And the solution is, you are given four options. Saturated, B supersaturated, C unsaturated, D concentrated. Please read the question again and again, pause the video and mark your correct answer. I will give the explanation for the correct answer. A saturated solution cannot dissolve any more solute at that temperature. If precipitation occurs, it is supersaturated. So option B is the correct answer. Next question. What is the mole fraction of solute in a 1.00 molar aqueous solution? Four options are given. Option A 1.770, option B 0.0354, option C 0.0177 and option D 0.177. You pause the video and record your answer. I will give the correct answer. 1 molar aqueous solution means 1 mole of solute is present in 1000 grams of water. Therefore, X of solute is equal to 1 divided by 1 plus 1000 divided by 18. That is equal to 1 over 56.5. Simplifying, we get the answer as 0.0177. This answer is available in option C. Please mark it. Next question. How many grams of concentrated nitric acid solution should be used to prepare 250 ml of 2.0 m HNO3? The concentrated acid is 70% HNO3. This is the question in NEET, was asked in NEET examination. So you read the question again and record your answer. Four options are given. 70 grams, 54 grams, 45 grams and 90 grams of HNO3. You have to make some calculations and mark the correct answer. So, therefore, M is equal to WB divided by W in B into 1000 divided by MB into volume solution in milliliters. Therefore, that is equal to 2 into WB divided by 63. The given values you have to put into 1000 by 250. That is equal to, from this you can calculate WB as 63 by 2 grams. Therefore, mass of acid into 70% into 70 divided by 100 equals 63 by 2. Therefore, mass of acid is equal to 45 grams. So, you please mark the correct answer as C. Next question. When the pressure is increased at constant pressure, so what happens? You have to identify. Four options are given. A. Rate of Haber's process decreases. B. Solubility of gas in liquid increases. Option C. Solubility of solid in liquid increases. Option D. 2 into Cs plus CO2 gas gives 2 CO gas and the reaction moves in forward direction. Which is the correct answer? You have to remember and answer. Solubility of gas in liquid increases on increasing the pressure according to Henry's law. So option B is the correct answer. Please mark it. Next question. A solution is prepared by mixing 8.5 grams of CH2Cl2 and 11.95 grams of CHCl3. If the vapor pressure of CH2Cl2 and CHCl3 at 298 Kelvin or the vapor pressures are 450 mm and 200 mm mercury respectively, the mole fraction of CHCl3 in vapor form is molar mass of Cl is given as 35.5 grams per mole. So we have to find the mole fraction of CHCl3. Four options are given. A 0.675, B 0.162, C 0.486 and option D 0.425. So make some calculations as shown in the inset box. Number of moles of CHCl3 are 11.95 divided by 119.5. That is equal to 0.1 mole. Number of moles of CH2Cl2 is 8.5 divided by 85. That is equal to 0.1 mole. Mole fraction of CHCl3 is Xa is equal to 0.1 divided by 0.1 plus 0.1. That is 5. Mole fraction of CH2Cl2 is Xp is equal to 1 minus 0.5. So therefore, P total will be equal to partial pressure of CHCl3 plus partial pressure of CH2Cl2. So that is equal to X into, we know from Henry's law, X into P naught C of CHCl3 plus XB into P naught of CH2Cl2. Substituting the values from the above, we get 0.5 into 200 plus 0.5 into 415. That is equal to 307.5 millimeters of mercury. Therefore, the ratio P of CHCl3 divided by P total, that is P of CHCl3 is 100 divided by 307.5, that is equal to, simplifying, we get the answer as 0.325. This answer is appearing as option D. Please mark it. This is a complicated, is a multiple and it is a time consuming. You have to remember and practice it. Next question. 18 grams of glucose, that is C6H12O6, is added to 178.2 grams of water. The vapor pressure of water in torr for this aqueous solution is, we have to calculate the vapor pressure from the given data. Four options are given: A 7.6, 76, 752.4 and 759.0. So you please calculate, pause the video, calculate and give your answer. I will give the solution. Number of moles of C6H12 and O6 are 18 divided by it is given 18 grams divided by total mass is, molecular mass is 180, that is equal to 0.1 mole. Therefore, the number of moles of H2O is 178 grams of water divided by 18, that is equal to 9.9 moles. The mole fraction of water in solution is 9.9 divided by 10, that is equal to 0.99. Therefore, vapor pressure of water in aqueous solution is, pressure of WA, water, is equal to P naught water into X water equals 760 torr into 0.99, that is equal to 752.4 torr. So this answer is appearing in option C. Please mark it. Next question. For an ideal solution, the correct option is, four options are given. We have to choose the correct option. Analyze and mark the correct option. Delta max of G equals 0 at constant temperature and pressure. All the four options are at constant temperature and pressure. Delta mix of S is equal to 0. Delta mix of volume equal to 0. Delta mix of H equals 0 at constant temperature and pressure. So we have to remember and mark the correct answer as delta mix of H equal to 0. Let it be option. The option D, you mark it correctly. You have to remember and mark. At 100 degrees, the vapor pressure of solution of 6.5 G of solute in 100 grams of water is 732 mm. If Kb is equal to 0.52, the boiling point of solution will be, we have to mark from the four options: 102, 103, 101 and 100 degrees centigrade as options A, B, C and D respectively. You have to calculate and mark the correct answer. So the calculations are shown. Mass of B is 6.5 grams, mass of A is 100 grams, PS is equal to 732 millimeter, and KB is equal to 0.52, TB naught is equal to 100 degrees centigrade, P naught is equal to 760 millimeter. So substituting in the formula, P naught minus PS over P naught is equal to N2 by N1, we can calculate N2. And from this formula, N2 is equal to 0.2046. And then use the formula delta TB is equal to KB into M. The delta TB is nothing but TB minus TB naught. That is equal to KB into M. The formula for M is N2 into 1000 divided by WA in grams. That is equal to TB minus 100. That is the boiling point of water equals 0.52 into 0.2046 into 1000 divided by 100. That is equal to 1.06. Therefore, TB will be equal to 100 plus 1.06. That is equal to 101.06 centigrade. That is almost equal to, that is equal to 101 degrees centigrade given in option C. Next question. Elevation in the boiling point for 1 molar solution of glucose is 2K. The depression in freezing point for 2 molar solution of glucose in the same solvent is 2K. The relation between Kb and Kf is Kb is equal to 1.5 Kf, Kb is equal to 0.5 Kf, and Kb is equal to 2 times Kf, and Kb is equal to Kf. You have to calculate and find the value of KBF in terms of KF. KB in terms of KF. So the given values are shown here. Delta TB is equal to 2, delta TF is equal to 2, M1 is equal to 1, M2 is equal to 2. Delta TB is equal to I, that Vanta factor, into KB into M1. Delta KF is equal to I into KF into M2. Given delta TF is equal to delta TB. Therefore, I into Kf into 2 is equal to I into Kb into 1. So, I and I get cancelled. Kb remains. So, that is equal to Kb is equal to 2 times Kf. This is option C. With this, we come to the end of this session on abnormal molar masses, as well as we have completed our cover unit 1, and next chapter will be, we will take up electrochemistry. Till then, goodbye.